right? This is chapter number 21 from your book. Okay, page number 88. Okay. Okay. Bismillahir Rahmanir Rahim. Now, what is a specific heat capacity? What is a specific heat capacity? Now, you can think, before I go into its definition, let's see. You can think of it as how much a substance can bear without screaming. How much a substance can bear without screaming. Like you are heating it, but the temperature is not increasing that much. Screaming, you can think of a screaming, you can think of raise in temperature as a screaming. Okay, so like you are providing energy, you keep providing energy to the substance, but the temperature does not increase that much. This is what specific heat capacity sort of means. Like, for example, this is a substance we're talking about. Now, we are providing energy to it by heating it. We're providing thermal energy. Remember, what was thermal energy that is getting transferred? The flowing thermal energy is called? The flowing thermal energy is called, what is that energy, thermal energy, which is flowing? Good job, Hala. Good job. Good job. I'm proud of you guys. Good job. You know how much it pleases me to see that, you know, you guys are learning and studying, and, you know, you're getting what I'm trying to explain you. So, you know, my hard work is bringing fruits. So when I can see that, it's very rewarding and pleasing. Yes, heat is that part of thermal energy which is flowing, which is moving. So yeah, so I'm providing it with a heat, a lot of heat is entering into it, but this substance is very patient. It is taking in heat and the temperature is not raising. The temperature is not raising, or even if it is raising, it is not raising too much. It is not rising too much, okay? So I am providing it with heat, but its temperature is not rising that much. That means this is a very patient substance. What sort of a substance behaves like this? What sort of a substance behaves like this? Like you're providing it with heat, but the temperature is not rising. What sort of a substance behaves this way? Now, I am not asking you to name the substance. I am asking you, yes, water is one of them, but yes, good job, Aisha Nadeem. Yes, insulator, good job. Yes, insulators behave that way. Like, because you know, what does an insulator do? You are providing it with energy, but it is not conducting. The atoms, the particles, for example, if this is an insulator, these bottom particles are receiving the energy, but because this is not a conductor, that vibration is not being transmitted to the other atoms. So these particles will keep vibrating back and forth and whatever, but they are not conducting this vibration onto other particles which are at the top of them, and therefore the average kinetic energy of this whole substance does not rise that much. It does not rise that much. Remember, what was temperature that we were measuring through the thermometer? What is temperature? What was the definition of temperature? Good job, Ajwa. Yes, this average kinetic energy. Yes, average kinetic energy. So average kinetic energy, so when the temperature is not rising that much, that means the average kinetic energy is not rising that much. Why? Because the particles are not conducting the vibrations along, and therefore the vibration of the molecules is not increasing that much. That means the average kinetic energy is not increasing that much, and therefore the specific heat capacity is high of insulators, okay? Water, by the way, is what? Insulator or conductor? pure water. I mean pure distilled water. Is it an insulator or is it a conductor? Is it an insulator or is it a conductor? Water. What do we expect? What do we expect from water? Will it conduct? Yes, Hiba, good job. It is an insulator. Yes, Hala, yes, yes, good job. And that is why water has a high specific heat capacity, because it is absorbing heat, but its temperature is not rising. Why? Because it is not transmitting that vibration along to the other molecules. Also, another thing, if the intermolecular, if the forces, for example, I'm making another diagram. If, for example, this is water, now I'm talking about water, these are water. Now, water is a special, again, my favorite polar water molecule, right? Now, because water is polar, by the way, we will talk about the polar molecules in detail in the next chemistry class. Because water is a polar molecule, therefore the intermolecular, what do I mean by intermolecular forces? Inter means between molecules. This means between, yes, yes. Inter means between molecules. Yes, Ajwa, good job. So these intermolecular forces in water are extremely extraordinarily strong. Why am I using extraordinarily? And extra strong, meaning stronger than other liquids. Stronger than other liquids. That's why. And so strong, I mean, these intermolecular forces are so strong and so, I mean, they are unique in the fact that these intermolecular forces you won't find in any other liquid. This is peculiar to water, which is responsible for the special behavior of water. Remember the special expansion and contraction of water that we did? Yes, that behavior also has to do with these intermolecular forces. These are called hydrogen bonds. These are called hydrogen bonds. I remember when I was in O-levels, I remember we had one whole chapter on hydrogen bond alone. I don't know where that chapter went now from the books, but I remember studying about these hydrogen bonds in great, great detail. This hydrogen bond is responsible for the unique behavior of water. And this hydrogen bond is also responsible for the extraordinarily high specific heat capacity of water. Okay. It is because it is these strong attractive, it is this strong attractive pull between the molecules which is not allowing the molecules to vibrate properly. And since they are not allowed to vibrate properly, they are like bonded and they're like bound to each other. Therefore, they cannot vibrate as much. Therefore, they cannot conduct as much. So even though you might be providing it energy, a lot of energy, but these molecules are so bonded, so strongly bonded to each other, they cannot vibrate too much. And therefore the average kinetic energy, which is measured by the thermometer, does not rise too much. Did you get my point? Yes. So that is why water has a high specific heat capacity. Now coming back to the definition of a specific heat capacity, another thing I would like to mention here is the word specific in physics. In this chapter, in this physics, means unit mass. When we're talking about unit mass, specific means we're talking about unit mass, any unit. It can be gram, kilogram, but the SI unit for mass that we are going to use in most of the calculations of this chapter will be kilogram, okay? So now let's read the definition of a specific heat capacity. It is the amount of heat a substance can absorb in order to raise the temperature by 1 degree Celsius or 1 kilogram. So again, it is the amount of heat a substance can absorb in order to raise the temperature by only 1 degree Celsius of 1 kilogram. So when we say something has a high specific heat capacity, meaning that it requires a lot of heat, it requires humongous amounts of heat to raise its temperature by only 1 degree Celsius of 1 kilogram, right? So I just came up with this. Okay, so we connected this with conductivity already, right? A good conductor's temperature would rise even with little heat. Now, if something is a conductor, for example, aluminum, right? And I am providing it heat, right? Now, of course, because it's a conductor, it would take no time for heat to travel all the way from the bottom till the top, and you won't be able to touch the top even after a few seconds of heating it because it's such a good conductor. Right, yeah. So the average kinetic energy of the atoms will increase in no time and with, with even a little amount of heat. Therefore, the specific heat capacity is low in this case, right? Meaning even less amount of energy would increase the temperature by 1 degree Celsius of 1 kilogram, right? So conductors have low specific heat capacity. Okay, insulators have high specific heat capacity. And okay, as insulators' temperature would not increase as much, even with a lot of heat, it would require lots and lots of heat to increase the temperature of a substance by just 1 degree Celsius, right? Okay. Okay, now the unit of heat that we will use in this chapter in IGCSE is joules. By the way, there are other units for heat as well, like calories. Calories is used in US. So if any one of you is interested in sitting for SATs, then in those calculations, you will be using this. But in IGCSE, this is the unit, okay, joules. Okay. Yeah, I don't know what went wrong with this setting for Zoom. Now it's asking for permission each time a participant wants to enter. Okay, now let's talk about the units of a specific heat capacity. Now, keeping the definition in mind, specific heat capacity is the heat required to raise temperature of 1 kilogram by 1 degree Celsius. So heat required in joules, okay? Mass, 1 kilogram is in kilogram, degree Celsius, right? So we get the units as joules per kilogram per degree Celsius. Now we don't use 2 pers usually. In symbols, we don't use 2 pers. This is not a correct way of writing units. So what do we do with it? Joules over kilogram, like per kilogram means over kilograms. So joule is the numerator, kilogram is the denominator, divided by degree Celsius. And now, can I write divided this way, multiplied by 1 over degree Celsius, or multiplied by the inverse of degree Celsius? And when I multiply them, I get this, joules per kilogram degree Celsius. These are the standard SI units that we will use in calculations. By the way, in physics, you should also be convinced regarding the units of any quantity. Okay, you should know how we got the units, the units that a quantity has, right? Okay, now I'm trying to prove this. I'm trying to prove this equation, okay? Let's talk about this. Let's say a substance has a specific heat capacity of 1000 joules per kilogram degree Celsius. Now, what does that mean? This means that to increase the temperature by 1 degree Celsius of 1 kilogram, I require 1000 joules heat, right? So this is the ratio method. To increase the temperature by 1 degree Celsius of 2 kilograms, I will require 1000 multiplied by 2 and divided by kilograms. So kilogram, kilogram get cancelled. This is the ratio method. I don't know if you guys have done the ratio method in your junior grades, but this is the ratio method that I'm using. So if for 1 kilogram, I require 1000 joules, then for 2 kilograms, I will have to use 2000 joules. I'm just multiplying 1000 joules by 2, right? Okay. And if I want to increase the temperature of that same 2 kilograms, so this time I'm keeping the mass constant, by 3 degrees Celsius. The same mass by 3 degrees Celsius, what will I do? I will multiply that amount that I calculated for 2 kilograms now by 3. Why? Because if I wanted to increase the temperature by 1 degree Celsius for 2 kilogram, I required this much, right? 2000 joules. So in order to increase the temperature of the same mass by 3 degrees Celsius, I'll have to multiply all of that by 3, right? And then I will get 6000 joules. Okay, that will be my answer. So what am I doing? What is this? What did I do overall? What's the gist of the story? The gist of the story is that the total heat required to raise temperature of 2 kilogram of this mass by 3 degrees Celsius is, I multiplied the specific heat capacity with the mass. This 2 was the mass. This 3 was the change in temperature. By the way, this small triangle that you see in books, and this means change. This is a symbol that means change. It's also called delta. So get used to this symbol. Okay, this means change. So specific heat capacity multiplied by mass in kilograms. Okay, the SI units will stay the same. And change in temperature. Remember, change in temperature. Okay, how will you calculate the change in temperature? Change in temperature, remember, is always, change in temperature is always calculated final temperature minus the initial temperature. This is how you calculate the temperature change. Okay, final temperature minus initial temperature should give you the change in temperature. Okay, so I now give this a formula form. C, symbol C is for specific heat capacity. M is for mass. Delta, I just told you, delta means change in theta. Theta again is a symbol which is used for temperature. Okay, delta means temperature, degree Celsius. Or if you are getting confused by this theta, theta is this. If you're getting confused, what symbol is used in your book? Yeah, they have also used theta. Your book has also used theta. Yeah, can you see? You zoom out, zoom in. Yeah, this theta. But it's okay. It's just a symbol. It just represents temperature. Okay, you can even use T. T. Many books are using T, simple T. T for temperature. So Q, that is heat lost or gained, is mass multiplied by specific heat capacity multiplied by the temperature change. Okay, now remember, theta means temperature. It's a symbol. It means temperature. Okay, degree, anything which is measured in degrees. Okay, now remember, we talked about heat gained, right? We did not talk about heat loss. Now, heat loss, same as heat gained, meaning you will treat heat loss the same way as you will treat heat gain. And the same thing will apply. Anything which has a high specific heat capacity, meaning that it requires a lot of heat to raise its temperature by just 1 degree Celsius, right? So that means it is absorbing a lot of heat, but without rising its temperature. So it will lose heat the same way, meaning it won't, meaning it will lose less heat. No, yeah, it will lose less heat. to decrease its temperature by 1 degree Celsius. Do you understand? Same way, anything that is absorbing slowly will also lose slowly. Anything which is absorbing rapidly or fast or quickly will also lose quickly. So that is why conductors cool down faster, right? Conductors also cool down faster than insulators. Now, insulators, first of all, will take longer to get hot. And once they are hot, it will take them longer to cool down. So heat loss and heat gain, both ways, the behavior will be the same of the objects or of the substances, right? I hope I'm making sense. Okay, then, okay. Then your book is talking about thermal capacity. Now, thermal capacity is same as specific heat capacity. The only difference is that, excuse me, the only difference is that this does not have the word specific with it, right? As you can see, the word specific is missing. That's because it is not talking about unit mass. I told you, specific in physics means unit mass, okay? Here in this thermal capacity, they're not talking about the unit mass. They're talking about the whole mass as a whole, right? And the temperature change they are, I mean, the thermal capacity is dealing with is only 1 degree Celsius. That's it. Okay, only 1 degree Celsius of the whole body. So this is defined as the heat required to raise temperature of the whole body by 1 degree Celsius. So therefore, in the equation, you will see that they did not, in thermal capacity, you do not have the delta theta. There's only mass and a specific heat capacity. So thermal capacity is only MC. There is no theta. Why? Because the delta theta is always 1 degree Celsius. So no need to write it, because anything multiplied by 1 is itself. So they did not write delta theta in this formula because it always deals with temperature change of only 1 degree Celsius. And mass is important because of the whole body, right? Okay. Since temperature raise is 1 degree Celsius in thermal capacity, and it is for the whole mass, therefore the formula is thermal capacity mass into specific heat capacity without the delta theta. And if you work out the units, mass is in kilograms, specific heat capacity, we figured out the SI units were joules per kilogram degree Celsius, right? Agreed? Kilogram will get canceled. And so you will be left behind with joules per degree Celsius, which is the SI units for thermal capacity. This is the SI unit for thermal capacity, joules per degree Celsius. Okay, there is no kilogram here. That's why it's not called a specific, because no unit mass here. Okay, let me move on. Now, physics chapters are real small, and this was not too hard and was a very short chapter. Compared to chemistry and biology, the chapters are really lengthy. They take forever. Right. Now, how to find a specific heat capacity by experiments. No, it hasn't finished. It's about to finish. Okay. Finding a specific heat capacity using experiments. Okay. Now, this, by the way, this experiment is included in your alternative to practical ATP. You will be required to know all of this. Okay. Now we know this formula, right? Q is equal to MC theta, whatever, or you can even call it MCAT, okay, for short, in order to remember. Q is equal to MCAT. Now, if we know all these other quantities, we can find out specific heat capacity. Now, the purpose of this experiment is to find out the specific heat capacity of a substance. Okay, your book has given examples of water and aluminum can. Okay, water and aluminum can. Now, water is an insulator, so it's got to have a high specific heat capacity, whereas aluminum is a conductor, so it will have a lower specific heat capacity. But in either case, we will use this formula to calculate this out, provided we know Q, we know M, we know delta theta, right? So what instruments will we use for each? This, we can use electric heater, okay? Now how? Because what do we want here? This is what? Heat gained, right? In the experiment, heat gained. This will be heat gained, right? How can we find heat gained? If we are using the electric heater, the power of which we know, okay, we can find out the power. If you do not know that some electric heaters have power labeled on it, so that will make your life easier. But if not, then you can immerse that heater into water, connect it to a 12-volt DC supply, and measure the current with the help of an ammeter. Okay, remember the DC, the voltage of the DC supply should be not greater than 12 volts, should stay, because we don't want large amounts of current, okay, because it can be dangerous for experimental purposes. So stick to 10 to 12 volts, okay, and then, you know, we will set a circuit and we can measure the current, which would be between 3 to 4 amperes. Okay, and then you can multiply them, their product will give you the power. Okay, once we know the power, okay, I hope you guys know these equations for power, these formula for power. This was in electric physics, or this was in first term. Did you guys do power in first term? Grade 7, yeah. Oh, okay, yeah, I don't remember exactly. Yeah, maybe in midterms or maybe in grade 7. But yeah, you have done power, right? Yeah, in grade 7, yes. Why are we finding power? Because we want to know, we want to have some instrument with which we can measure the heat that we are providing to that substance, okay? Because we want to plug in figures into this formula, because we want to use this formula to find out the specific heat capacity of a substance, okay? So this is one way. If we are using an electric heater, we can get around to the energy or the heat transferred via power. Because remember, these are the two equations of power. Once we calculate the power by multiplying volt with the current, we can then use this equation. Remember, power is the rate of work done, rate of energy transfer, if you remember. So energy transferred divided by time taken. If you cannot remember, go back and you can read that chapter real quick. You can have a recap and then it will come back to you, okay? So if we have power and if we multiply that by time, we can get energy transfer. See, this is our purpose, okay? We are trying to get heat gained. Like how otherwise can we measure how much heat we provided to a substance? Remember, see, what are we trying to do? Okay, okay, for example, this is the substance, this is water. Okay, we are trying to measure the specific heat capacity of water, right? We know this is the formula. Okay, we read in the book. Okay, we know this is the formula. We want to find this out. Okay, if we want to find this out, we should know this, this, and this. This is heat gain, this is mass, this is temperature change. Temperature change is easy. We can measure by thermometer, final and initial. The difference will give us the change in temperature. Mass, we can weigh out. Heat gained. How? Now, if I am heating with the help of, for example, you know, some flame, if I'm heating with the help of flame, Bunsen burner or whatever, you know, my heater or my whatever source of flame is, how will I measure how much it is? How will I measure how much it is? So we have come up with this idea. Let's use an electric heater. Okay, let's use an electric heater. If we know its power, we can find out the energy transferred. That will be the heat gained. That will be the heat provided. Did I make sense? Now, did you understand? See, look at this picture. This is what they're doing. This is water. This is water in a container. And instead of using that flame, he's using this electric immersion heater. Why is it called an immersion heater? Because we are immersing the heater in the water, right? And remember, the heater should not touch the bottom, but it should be as low down as is possible. Why? Because we want the whole water to be warm. If the heater is just floating on the surface, the top water will be warm, and you know warm water is lighter, it won't sink. Okay, it won't sink, and there will be no convection currents, and the surface water will be warm and the bottom water will be cold, and therefore there will be uneven temperature, okay, in the water, and that will affect our results. So the whole water should be at the same temperature. The whole water should have uniform temperature, right? In order to make sure that the water is uniform throughout, I mean, the temperature is uniform throughout the water, you have to do two things. One is to keep the electric heater deep down, but it should not touch the aluminum. Why? Because we don't want direct conduction of heat to the aluminum, because remember, aluminum is a very good conductor. And yes, we should stir the water. Yes. And I would not recommend that you stir with the thermometer. Stir with a separate stirrer. Because if you stir with the thermometer, I think that would also affect its reading. Yes, a glass rod. Yeah, because the rod itself is a conductor. So glass rod is best, right? Now, so you understood. I hope now this made sense. Why are we using electric heater? And is there any question? Then you can ask me in the chat window. Okay, now mass of water. Now the most accurate way of putting in water is that you should weigh this aluminum can before adding water, empty, when it is empty. Before adding water, you should weigh this aluminum can and then weigh it again after you have added water. If, for example, you want to add 1 kilogram of water, add 1 kilogram of water, but then weigh it after you have added the water. And then you subtract the mass of empty can from the filled can, and you will get the mass of water. Are you getting me? Okay. Here. Okay. Okay. This is called the tare weight of water. What is tare weight? See, we weigh the aluminum saucepan, then we add almost 1 kilogram of water into saucepan and then weigh it, and then we subtract the weight of the aluminum. We subtract the weight of the aluminum saucepan from the whole to get the exact weight of only water. This is to subtract the weight of the aluminum can from our results. Okay, this is how you can weigh the water. You can make sure that you have exactly 1 kilogram of water. Okay, another thing, the more precautions you will take to be exact, the closer your results will be to the actual value of the specific heat capacity of water. Remember, the purpose of this experiment is to calculate the specific heat capacity of water, which is how much? Which is 4,200 joules per kilogram degree Celsius. That's the specific heat capacity of water. Now, remember in this power, we also had time taken. So now power, I have replaced power by this. Sorry, I have replaced Q by this, power multiplied by time. Okay, because this is what I actually have. I have the power of the electric heater, and I can measure the time period with the help of a stopwatch. Okay, as soon as I turn the electric heater on, I will switch on my stopwatch. Okay, I will also share a video. You know, there's a student who is actually performing this experiment, and this is a GCSE student. Okay, it is posted by some school, some UK school. I like that video a lot, and I will share it with you guys after this class in the group. Okay. Amina, how do we get energy? Yeah, by multiplying power with time. By multiplying power with time, you will get energy transferred. If you remember, power is the rate of change of energy or rate of energy transfer. So from that equation, we got this. Okay. So MC, okay, tare weight, I explained you, and then I will keep the electric heater on for only 5 minutes. So as soon as I turn the electric heater on, my stopwatch should be on as well. And then right exactly at 5 minutes, I will turn the electric heater off and the stopwatch off as well. Okay, stirring water is important. Why? We just discussed, so that the temperature is uniform throughout the water. Note the highest temperature recorded by thermometer. Why highest? Why highest? Because you see, if the temperature is any value other than highest, then maybe the water was not well stirred, or maybe the water had not absorbed as yet properly enough. You did not allow enough time. So that is why within that 5-minute time period, we will record the highest temperature. We will wait for the water, the temperature to be stable. Stable mean, like, we cannot record a rapidly fluctuating temperature. We cannot be recording mercury level, which is going up and down, rapidly and fluctuating. We will wait. We will record that temperature where the mercury level is a little stable, is a little steady. Steady is where it stays. Are you getting me? Okay. Yeah, these are all little practical details which are required for you to understand. Okay. Okay, wait. Okay, now, so after you have done all of this, keep this picture in mind, okay? You will calculate with the help of this power and time, you will get the heat gained. You have the mass of water, you have the temperature change. You plug in the values, and then you can calculate the specific heat capacity of water. Now, I want to ask you, what is the biggest assumption we made in this whole experiment? What is the biggest assumption that we took in this whole experiment? And another thing, do you guys have any question for me? Can we use a measuring cylinder instead of aluminum can? Yes, you can use measuring cylinder. In fact, I think that would be even better than aluminum can. But make sure that the water temperature is not too hot to break that measuring cylinder. So yeah, just make sure. How do we get the power? Power would be labeled on the electric heater, and if it is not labeled, I told you that another way of finding out the power of an electric heater is to connect it, first immerse it in water and connect it to a 12 volts DC supply, and then measure the current with the help of ammeter, and then you multiply the voltage with the current. And using this equation, look at this, using this equation, when you have the current, you have the voltage, you can multiply them and you can get power if power is not already labeled on the electric heater. Okay. What? Good job, Ajwa. Good job. Yes. Assumption is that there is no heat loss to the surrounding. Very good. Is it important to use aluminum can? No, Atika, no, not at all. In fact, we are just about to discuss what are the flaws in this experiment. What are the flaws? First, I wanted you to tell me the big assumption that we took in this experiment, which was, yes, Ajwa. I think Ajwa is one of those girls in this group who is preparing before coming for the class and who is also reading after the class. You know what? I can tell who is reading and who is not reading. You know, when I had this chemistry teacher, he could also tell. He could tell that, you know, a particular student is studying and he's doing reading and he's listening to my lectures carefully. And not only is he listening, but he's also following it, like, you know, reading and studying it after the class. Because only those students are able to answer those questions which a teacher emphasizes on, you know, and that person knows. So because Ajwa is able to answer this question, I know she read the book. Yes. Okay, so why are we using aluminum pan? So yeah, aluminum now we will discuss. This is an error, by the way. We shouldn't be using an aluminum pan. And you tell me why. You tell me why. What is the use of specific heat capacity? Yeah, we will come to that later. Okay, can we use, okay. Yes, BI is the voltage and current, right? Why not touch the bottom? Because if the electric heater touches the bottom, it will be directly conducting the heat to the aluminum can without heating the water. And so now we are measuring the heat which is delivered by the electric heater, but that heat is not being absorbed by the water. It is being conducted away to the aluminum. So that will be an error in our experiment. So we are thinking that, you know, all this heat which the electric heater is giving, that we calculated by multiplying voltage and current and by all these formulae, all this heat did not, got conducted away through the aluminum can without actually heating all that water. Okay. Okay. What does, okay. Now tell me, good conductor. Yeah, yes, Aman. Who said yes? Yes, aluminum is a good conductor. And so, yes, Atika, good job. We should not use aluminum can because it is a good conductor. And so it will conduct the heat away without giving time to the water to raise its temperature. Yeah, Amina, she is reading. She is reading. Intelligent, yes, of course she must be, but you know, the thing is that she's reading. That's why. Yes, it will conduct heat. Yes. So yes, we made the assumption that whatever heat the heater is providing, the water is absorbing it. Yeah, this is the assumption we took. Now, why is our assumption flawed? Why is this assumption, you know, not good? Is it true that whatever heat the heater is providing is being absorbed by the water? Is that true? Yeah. Why? Why? Dispersing? Is it true that whatever heat the heater is providing, the water is absorbing all of it? If no, then where is it going? Yes, some will be conducted away by the aluminum. Good job. Yes. Any other mode of loss of heat? Yes, some will be lost to surrounding air. Yes, by convection and by conduction and by radiation, right? All the three ways. We should use black containers. Black containers will absorb all the heat, right? Yeah, so black container I think would be, they will absorb all the heat. So that would make our results even worse. Amina, I think we want something that will not absorb. We want insulators. Yeah, we want insulators. Yes, evaporation will also affect. Good job, Atika. Yes, good thinking. Yes, evaporation. And you see, as we are heating, there's evaporation also going on, right? And that evaporation will also require heat. So it's taking away that heat and it's cooling the water down. So that is another flaw. Okay. So how can we fix these flaws? By using insulators, by using a lid to prevent convection and radiation to minimize. We cannot, you know, completely get rid of this. And yes, also get rid of evaporation by using a lid. And by using, you know, some insulator, we can surround this can by a styrofoam maybe, or we can use an insulator. Yes, so aluminum can is a bad choice, I think. Yeah. Plastic, yeah, be careful because plastic melts as well, so be careful. Yeah, okay. Yeah, okay. Yeah, if the temperature is not too high, we can use plastic. Yes. Okay. Now, how do we okay, are there any other possible errors? Are there any other, what are the other possibilities of errors in this experiment? See, I'm discussing all of this from alternative to practical point of view because they ask such questions. They should think before the experiment. No, they did it on purpose. They wanted you to think. They want you to think. So if for example, we do not have an insulator available and aluminum can is the only thing we have. Now, when we can use it, we should use an insulator to avoid loss of heat. Yes. Yes, thermometer should not be used as a stirrer because if you are moving the thermometer, you will affect the level of mercury. Do not use thermometer as a stirrer. Use another separate glass rod, okay, to be on the safe side. Right. What other? Yes, yes, okay, yes. You're telling me the possibilities of error. Yes, okay. If you're using thermometer as a stirrer, so that would be a flaw. And what else? Parallax error while reading the thermometer, right? And what else? Zero error in weighing the water. Yeah, zero error on the, you know, weighing machine or the weighing balance. And what else? What other possible errors you might have? Stopwatch, maybe you got delayed. You switched on the stopwatch a little late, a few seconds, a few milliseconds, or you turned it off a few milliseconds earlier. You know, these are all human errors. Humans are prone to make errors, so we will allow for these errors. Okay, what else? You know how I am suggesting the errors? I am looking at the formula and I'm looking at how I measured each and what possible errors I might make while measuring the temperature, while measuring the mass of water, you know, in the electric heater. Okay, yes, and also look at the instruments. What are the readings you're taking? What are the instruments you're taking? Think about all of this. What are the possible errors you might? Okay, picture yourself in the lab. I will share a video of this experiment. Okay, now if we want to find out the specific heat capacity of aluminum, now that was water, right? Aluminum. Now this is a solid and this is a good conductor. Yes, and things should be clean before using them, right? The aluminum can should be absolutely dry before you add any water. Yeah, and that is why we use tare weight. Why do we use tare weight? Why don't we just directly weigh water? Is because some water might be left behind in the can in which you weighed, or there might be some droplets of water already in the saucepan. To get rid of all those errors, we take the tare weight. It's called the tare weight. Okay. Now, finding a specific heat capacity of aluminum can, which is solid. Again, we will use the same formula, same measurement, same sort of electric heater, connection with 12 volts DC supply, all of that. Okay, again, but the only difference is that this time we have solid and we don't have any liquid. Okay, there are two holes. Yes, SHC is for specific heat capacity. Yes, Atika. Okay, so now we have two holes. One is for the thermometer, the other is for the heat, for the electric immersion heater. The rest of the whole process will be the same, will stay the same. Again, we will wait for the temperature to be steady, stable. Meaning to say that you cannot measure rapidly fluctuating mercury levels. You have to wait for the temperature to be a little stable, little more steady. Highest value, because lower value may be due to non-uniform distribution of temperature through the water, or maybe the water has not absorbed heat enough. Okay, so you have to wait. Okay, what is the possible, now we already discussed all the possibilities of errors in case of water. Same possibilities apply here as well, except for that there's no stirrer and there is no uniform, non-uniform problem here. But there is one other different problem due to the fact that this is a solid. Yeah, and there is no evaporation problem here. Yes, good job, Ajwa. What else? What else? Think, what other possibility of error in this case? Yes, Sandhu suggested something. I, okay, think harder, and I'm giving you a hint. Look at this closely. Look at the diagram closely. I'm giving you a hint. No, Ajwa, no. Aluminium will not melt. Aluminium is a metal. It has a very, very high melting point. Its melting point is above 1,000 or something. It's a metal. What are your, yeah, you're right. No lid issue, right? Yes, good job, Myra. Battery voltage, great amount of heat loss to environment. Why, Amna? Some of the, it will conduct heat. Yes, it will conduct heat, but this time we are measuring the temperature of aluminum itself. So that's not counted as a flaw, okay? I mean, you see, in the previous experiment, we were trying to measure the specific heat capacity of water, but aluminum was interfering. Here, we are only measuring the specific heat capacity of aluminum itself. There is, what might be interfering here? What is interfering here? Yes, good job. Sundus answered. You guys tell me. What's in the hole, Maruj? You're close. Yes, Saad Amir, you're close. Extra space. Air. There you go, Ajwa. Air. Yes, there is air between the thermometer bulb and the aluminum can. Can you see that? Yeah, because of air, and air is an insulator. Air is an insulator. Okay, you can see that it's not dipped as, you know, as it's dipped here. So we know there is no air between the thermometer bulb and the water, but here there is. So what we do in order to know oil, hala, if we add oil, is also an insulator. Hala, oil is also an insulator. Remember, it does not have any charged particles. It is non-polar. Oil is non-polar. Okay, so yes, there is air, and air is an insulator. Is add that we add a few drops of water and tap water, because tap water has a few ions, so they will be able to conduct and therefore give us. Now, this is not perfect. This is not perfect, but this is the most you can do. So you can minimize that error by just adding a few drops of water. Okay, it has tap water has a lot of ions, and the ionic concentration varies from place to place. No need to worry about that. But yes, yes, a few drops of water is how we will deal with this problem. But if there is only air, then air itself is an insulator. So that would be a problem. It would affect the rereading. Okay, that was the thing here. Okay. Then we move on to the importance of a specific heat capacity. Importance of the high specific heat capacity of water. How does it help? Now, we talked about the hydrogen bonds, remember? And so we know why water has high specific heat capacity. But how does this help us? Now, I told you anything that is taking in heat, but its temperature is not rising, that means it is taking in heat very slowly, meaning, you know, like taking, but its temperature is not rising. So same will be the case with its losing heat. If it is taking it in heat slowly, it will be giving away also slowly. So water is the same. Now compare the specific heat capacity. Yes, good job, Hala. Yes, insulators gain and lose heat slowly. Think of conductors as, you know, good pathways of heat, you know, like good heat pathways. They get in, get out real easily. Insulators are like obstacles for heat. They don't get in, and when they get in, they cannot get out. Well, I mean, the heat cannot get in, and once the heat gets in, it cannot get out. Think of insulators that way. So pure water, water on the whole, is an insulator. If you compare it with soil, look at the difference. Specific heat capacity of water is 4,200 joules per kilogram degree Celsius, whereas a soil is 800 joules per kilogram degree Celsius. And how much time is it? Yes, yes. Yeah, but yeah, I'm talking about heat here. Yeah, soil is, yes, soil is a conductor, and especially compared to water, it is a very good conductor. Okay, you can see the difference is 5 times. 8 5s are 40, right? If you divide 4,200 by 800, you'll get 5 point something, 5.2 something, right? So that means the water requires 5 times as much heat as soil to raise its temperature by 1 degree Celsius only. Do you understand this? Okay, how should I, okay, can you give me a piece of paper? I want to draw a diagram. Give this piece of paper to me. For example, this is C and this is water. Okay, now this would require 5 times heat compared to water to raise its temperature by only 1 degree Celsius. Only this much heat will raise its temperature. Oh, what did I write here? Land, sorry. Yes, land. I'm sorry. Yeah, so the water requires 5 times as much heat to raise its temperature by 1 degree Celsius as compared to land. Right? Now, no, I'm not, don't confuse yourself with impurities right now. Forget the impurities, okay? We're just talking about water. Yes, I know this is not pure water, but we're just talking about water right now, okay? And compared to soil, it has a higher specific heat capacity and it is an insulator compared to the soil, to the land, okay? Just keep yourself here so that you understand what I'm trying to say. So in summers, the temperature of water will not rise as much as the water would. I mean, sorry, as the land would. I don't know why I'm saying water again and again. So yes, the land temperature would rise very quickly compared to water, right? And the water temperature would not rise that much. Therefore, in summer, the sea would be cooler. In summer, the sea would be cooler compared to the land, and this would be warmer in summer. And therefore, in summer, the coastal areas are pleasant because you can feel the cold breeze in, right? Okay. Then it also has to do with pressure differences, cooler air, higher pressure, warmer air, less pressure, and the air flows from high pressure to low pressure. So you have cool breeze coming in from the sea. So it's very pleasant in coastal areas. And even on islands, you know, islands which are surrounded by sea on all four sides, right? They're even more pleasant. And in winter, it's the opposite way. In winter, now whatever heat the water absorbed throughout the summer, it will be losing it. Now just as it was sluggish in absorbing, it is sluggish in giving it away. So it won't give away that much as the land would. So the land would be cooler. In winter, the land would be cooler. If this is the sea and this is land, okay, in winter, this would lose less, this would lose more. Okay, this would lose more. And this won't. So this is warmer. And this is very cool. Yeah. And so in winter, the pressure here, cool air, higher pressure, warm air, less pressure. And so the wind will blow from the land towards the sea. Right? So in winter, this is because of this sea effect, the coastal areas are warmer compared to the inland areas. Inland meaning deep into the continent, like really away from the sea coast. Right? So this is called a sea effect or the coastal effect, right? Now, islands, what happens in islands? Yes, what happens in islands? Now, islands in summer, the water is cool, right? And so it is pleasant in summer. It doesn't get too hot because of the cool breeze from the sea. In winter, I mean, the temperature of this land never rose that much, and then the winter approached, and when the winter approached again, now the sea is warmer, and so the sea never allows the temperature to go too low or too high. So throughout the year in islands, the temperature is really pleasant and moderate. So that's why you have, you know, those tourist resorts on islands, and islands are really beautiful and everything. So yeah, that was what your book was talking about. And yes, in what other way is this high specific heat capacity of water useful for us is that it is used as a coolant for engines and radiators. Why? Because the water can absorb a lot of energy without its temperature going too high, and therefore it reaching its boiling point. So it can absorb, yes, I know, Atika. So I'm just about to wrap up. So the water can absorb a lot of energy without boiling away. Okay. And why is cooling required for engines? Because too high temperatures can damage the parts of engines. Okay, by the way, those students who are bothered by, you know, a little extension of my lectures, you know, they're just free to leave. Okay. No, it's okay, Atika, it's okay. The only thing is that, you know, I'm just trying to, you know, oh yeah, you're hungry. You know what? I'm also hungry. It's okay, it's okay. Now, do you guys want me to do these? These are only 3 questions. Okay, let's just, you know, get them over with. Okay, because I don't want to leave this behind. Okay, how much heat is needed to raise the temperature by 10 degrees Celsius of 5 kilogram of a substance of a specific heat capacity? What is the thermal capacity of the substance? Remember the thermal capacity formula? It does not require the temperature change, mass multiplied by the specific heat capacity. So let's do this. Do you have a calculator? Okay, mass is what? 5. and a specific heat capacity is 300. And so it should be, how much heat is needed to raise the temperature by 10 degrees Celsius of a substance? What's the answer at the back? Tell me the answer at the back. 21. Real quick, real quick. Yeah, Hiba, 1500 joules. Even I was getting 1500 joules. This is chapter 21. Chapter 21. Yeah, 1500. Oh, okay. Joules per degree Celsius. Why have they given two answers? How much heat is needed to raise the temperature? Oh, there are two questions. Okay. How much heat is needed to raise the temperature by 10 degrees Celsius of, okay. What is the thermal capacity of the substance? Oh, okay. Yes, so thermal capacity is 1500. Okay, thermal capacity is 1500, but how much heat is required will be done this way. MC delta theta. Okay, so this is Q, we have to find out. Mass is 5. Specific heat capacity is 300, and the, okay, yeah, so yeah, we got it. This was easy. Okay, you got it, right? Everybody got it. Okay, move on. Question number 2. The same quantity of heat was given to different masses of 3 substances, A, B, and C. The temperature rise in each case is shown in the table. Calculate the specific heat capacities of A, B, and C. Oh, okay, so you just use Q is equal to MC theta. Okay, you have the M, you have the Q, you have the theta. So plug in the values and you'll get it, okay? Okay, I don't think I need to do this. This is really easy. The jam in a hot Pop-Tart always seems hotter than the pastry. Why? Who will answer this? The answer written at the back. Question number 3. Okay. Now, okay, another thing. Whatever seems hotter means that it is a conductor. It is releasing energy, right? Really fast, right, Amna? So means hotter means like it is conducting heat. That is why you're feeling hot, right? So if it is conducting, that means its a specific heat capacity should be lower. So I think the hot Pop-Tart should have a lower specific heat capacity than the pastry, right? Or the other way around. The same thing. You can even say that the specific heat capacity of the pastry is higher than the hot, whatever that is, tart, hot Pop-Tart. Okay. Okay. Is there any question? I wanted to do past paper questions, but you know, again, we are out of time. So you know what I'm thinking, because we don't get time, because we have only 1 hour class and I can only do explanation. I don't get time for questions, though I would love to do questions with you guys. And yes, we will also do ATP if we can. Okay, but the thing is that after we are done with the course, after we are, you know, like finish the course, then we will do questions, inshallah. Okay, but we will not, I mean, I will not continue with these classes during Ramadan. Yeah, this is what I thought about. And yeah, in Ramadan, I will not continue with this, but after Ramadan, yes, inshallah. Okay, after Ramadan. Okay, because you know, in Ramadan, I don't know, yeah, we should dedicate more time to our ibadat, and you know, yeah. Okay, so okay, jazakallahu khairan. Yeah, in Ramadan, I'll take a break in Ramadan. Okay, you guys too, because of the Taraweeh and everything, and we will be fasting during the day. So inshallah, after Ramadan, and I will try my best to cover as much as is possible before Ramadan, inshallah. I have no idea about the final exams, no idea. Yeah, but yeah, we will be offering Taraweeh at home, right? So yeah, but we will be offering Taraweeh at home, inshallah. May Allah help us. Okay, then tomorrow we are going to do, okay, tomorrow I'm going to take chemistry class, okay? Chemistry class, and we will do questions only tomorrow. Chemistry class, questions only. I have pulled out questions for you guys. And we will do polar molecules. Okay, I want to take, I want to discuss a little about polar molecules, and we will do questions. And after that, we will start that quantitative analysis chapter of chemistry. Yes, and after all the chapters are done, then we will do, we will start with past papers, right? Yes, after we are done with the chapters, then we will start with past papers. Okay, if you guys have any past papers with you given by your teachers, send me or share in the group, whatever, and then we will discuss them and solve them together. If there are any worksheets given you want me to help you with, you're most welcome. Okay. Okay, question 1. Okay, Amna. Okay, Amna, I'll explain you privately. Okay, question number 1. Okay, Arham, no problem. Electrolysis we will do. We will do a lot of electrolysis questions. Don't you worry. Did we do chapter 19 of chemistry? What is that chapter? Give me the name. I don't remember the numbers. What chapter are you talking about? Physics, chapter 19. What is it? Chapter 19 is chapter 19. Yes, I have done expansion of solids, liquids, and gases. This was one of my first classes. This was one of my first classes when the school had not started its online classes. That's when I did this expansion of solids, liquids, and gases. Okay. So yeah, I have done. But I'm sorry, I don't think I have the recording of that class because at that time I did not have the recording facility. Yeah, but inshallah, no problem. We'll revise. Okay, we will revise. Okay, assalamu alaikum. Okay, assalamu alaikum wa rahmatullahi wa barakatuh. Allah Hafiz.
Allah Hafiz, ma'am.
Allah Hafiz, teacher. Allah Hafiz.
Joshua.
You're most welcome.